All right, hello everyone, and thanks Helen for an amazing introduction. um, Let me just share my screen. Okay, and wrong button. Okay, can everyone see the slides? Okay, cool. So today I will talk about greedy algorithms, and this is something that I really like to talk about because yeah. So first of all, what is a greedy algorithm? So it's a way in which we build up a solution by choosing the best option or whatever is the available at every step. So this is also something that I recently thought about. Like I always thought greedy algorithm is a type of algorithm, but it's actually a technique. It's a way of thinking about a problem. Um, so the thing about greedy algorithms is it tries to do the solution in one pass. So if you have like a bunch of options to choose from, you just do it step by step, but you never, you wouldn't backtrack, if you will. So backtracking is actually a different technique, which we can touch on a different topic and in advanced algorithms. So how do we think about greedy algorithms? So we said we want to think about the problem step by step. So let's look at this example. So this is the first example. I'm just going to call it tasks. And so say you have a list of things to do with start and end times. So what we want to do, and this is like a common problem for, I guess, everyone who works in tech. You have loads of things to do. You can only do them once, one at a time. You can't be both reviewing pull requests and writing tests at the same time. That's just, how is that possible? So what we want is to be able to select the most number of tasks that we can do, done by a person, assuming that a person can do only one task at a time. So if you look at this example, we have a list of objects, which is called a task, and it has the name of the task, the start time, and the end time. So here we just simply, to simplify the problem a little bit, we represent them as integer values. And so you can see here you have a task called review PRs, which starts at time 10 and ends at time 20. We have a task called write tests, which starts from time 12 to time 25, and another one called eat lunch, which starts at time 20 and ends at time 30. So here we have a list of tasks, and we said we can only do one at a time. So if we look at the tasks here, we can see that some of them have an overlap. So like review PRs and write tests, their start and end times kind of overlap over each other. So that means, we probably can't do both of these things because we can only do one task at a time. So how do you go about thinking about this in a greedy algorithm way? So I just kind of made a visual representation of the schedule, right? So as I mentioned, we have write tests. It kind of overlaps with review PR. So we probably can't do two of these. And so intuitively, what I'm doing here is I'm looking at each task and I'm looking at their start and end times. So how can I make up my schedule, right, in such a way that I can do the most number of tasks that satisfies this condition? So one way to think about it is, well, I'm going to take all the tasks, right? I'm going to look at all the tasks and see when they start and when they end, right? And that's one property of this problem that we said we can only do one task at a time. So that immediately tells us that if a start time of a task is sometime between a start and end of any of the other available tasks, you can immediately rule that out, right? So, and then you do it again for every task that you see in your to-do list. And this is how you want to think about greedy algorithms. You want to do things step by step, and at every step you have an option to choose what is best to do here. So how do we go about this? Like, how do we want to make our decision? So that's the next question here. We now have a kind of a rough idea of what steps we want to take. We want to pick which task to put in the schedule, right? So, and then what's the criteria for us to make a decision? So we said overlaps, right? So if you think about it in a way that, you know, this one starts at 10 and ends at 20, and the other one, eat lunch, ends at 20 and starts at 30. So that means these two things you can do given a schedule. So immediately you can think, well, 20 is a property of these two tasks that, you know, we can kind of consider to say, this is how I'm going to choose what to go for. And so then you go, okay, it sounds like if I just pick the tasks that are closest to the end time of the first task that I pick, I kind of optimize for that. Another thing to think about in here is that these are time values. That means that they are increasing in value. So that means, you know, think back to our previous topics about sorting. That means this is something that we can sort, right? These values are something we can sort. So now I kind of like thinking about the solution, we end up with something like this, right? So we consider the end time when we look at it, which are the things we can do on the same day. It's when they don't have an overlap. So I guess how we want to go about it, we pick the task whose finish time is the earliest, because that's the first task we want to do, because we said time is increasing in value. And then for each task in this list, we want to pick the task whose start time is greater than or equal to the finish time of the previous task. So we said we want to pick the task here that finishes the earliest, which is here. And so what's our next step? We want to pick the next task. And for that, we want to make a decision. So which is the start time that is closest to this point. So here we go, eat lunch, right? So obviously we cannot pick this because the start time of write tests is earlier than 20. So it's less than the end time, the task that finished earliest. So what does that look like? So we've kind of translated that. We have this idea and we want to translate that into code. So here we have it. So we said, pick the task whose whose finish time is the earliest. So how do we find out the task's finish time is the earliest? So I guess, you know, we want to sort it by end time, right? So then we sort the tasks, and then immediately if you sort the tasks, the first item in your list, so you have your list of things and you're going to go through them. Your first list is obviously the task whose finish time is the earliest, right? So here it is, we pick the time whose finish time is the earliest, and so I add them to my lists of possible tasks. And so for the rest, right, so if I'm going to go through the task, and when I encounter that task, I then say, well, is the start time of this task that I'm looking at greater than or equal to the previous end time that I've just looked at? If it is, I add it to my schedule, and do it until I've gone through all the tasks. So this is how you think about greedy algorithms. You kind of come up with a way to group your items in some sort of list which you can go through. In some cases, it might not be a list. It could be an array. It could be some other data structure that you can think of, and you want to go through these items and effectively make a decision. Am I going to go with this or with that? And in this case, we considered the property of the task, which is the start and end time of these tasks. So does that make sense? Are there any questions? So greedy algorithm can be applied for interval merging type of problems. I'm not quite sure about the answer to this question. I think greedy problems are, they might be useful. Okay, sorry. They might be useful for when you want to come up with the best, if you're avoiding overlaps, for example. In this case, this is one example. So I'm going to talk about more examples so we can kind of start to recognize what kinds of problems we can apply greedy problems to. So here's another example. This is something that is quite familiar to everyone, I guess, unless you've just been using contactless all the time, which I guess is the case for in the last year or so during the pandemic. But imagine pre-pandemic times and we still carried cash around. So if you're trying to give change, and this is like a super common kind of problem of a pattern of problems. So you're trying to give 67 pence in change. So I'm going to talk about pence here because I'm here in the UK. So I mean, how do you go about it, right? Like, just think about it. How do you give change? Obviously, you want to be polite and not rude by not giving like a massive bag of coins to the customer, right? So that means you want to give the least amount of coins to the customer to give 67p in change, right? So how do we go about it, right? So we have denominations of coins. So here in the UK, we have a £1 coin, a £2 coin, a 50p coin, a 20p coin, a 10p coin, and a 5 and a 2 and a 1. So those are the available coins that we have here that you can, and in this case, assume we have infinite amount of coins. We don't have to worry about how many coins are there, right? So in this case, and I think this is quite important when you're, especially for when you're in a algorithms interview, for example, you can make certain assumptions about a problem. So here, I'm just explicitly saying that here we don't have to worry about however many coins there are. We can assume there's infinite amount of coins. So I think how you go about it is you get the coin that has the biggest denomination, right? So that you can have the least amount of coins to give back. So you get the biggest coin, C, available from a denomination set D, which is the coins in the UK that I've just described, such that your biggest coin is less than the change you need to give, right? And then for every coin that you give to a customer, you subtract that from your change amount and you repeat until the change is 0. So again, you see a pattern here where you have an array of options. You have a number of coins you can choose from to give change, but you make a decision which coin to go for. And in this case, we just pick the biggest coin available that is less than the amount that you need to give. So what does that look like in code, right? So we said we want to get the biggest denomination from the set of coins that we have, right? So again, very similar approach to the tasks problem, right? We have a list of things which is, in this case, it's a property of what we make a decision on, right? So then here I sort the denominations so that I get the biggest coin from this set every time, the biggest coin that is less than the change. So in the example we have is 67p, right? So here, if we go, well, here we just handle some simple cases where if the change is zero, just return straight away. But here, while we have some change to give back, while we have some amount, we go, 4 coin in denomination. So we're going through our set of coins that we have to make a decision on, right? If the change is bigger than or equal to the coin, then you can give the coin. So this is and then I put it to the bag of coins, and this is the bag of coins that I return, right? So when you look at this problem, it's very similar in the sense that you are going through a list of possible options, and at every step, right, at every step in your loop, you make a decision based on what information you have on hand. In this case, the remaining amount of change you have to give, and the coins that are available for you to pick. And in this case, if you look at the complexity here, you have the sort. You have to consider the time complexity of the sort, which I think this is n log n, where n is the available denomination. So here we have several, so this is your n. The worst case version of this problem is if your denomination is just, say you only have 1p coins, then you don't really have a choice, right? You can just give 1 coin. So that is that. But so here's the thing about greedy algorithms as well. So greedy algorithms is something that's quite intuitive to think about, right? So here we go, right, I just need to pick the biggest coin, compare that to my price, and just give it a go, give the change, right? But we have to be careful when we think about greedy algorithms. And this is also especially important when you're, again, in an algos interview situation, you think about your edge cases. So edge cases mean, well, what if in the worst case, we said, worst case, it performs, if you only had a 1p denomination. But actually, what will happen to this algorithm if you didn't have a 1p denomination available from your set of coins, right? So what will happen here? Any ideas from the audience? What will happen to this algorithm if we didn't have a 1p denomination? So if we didn't have a 1p denomination, which is the smallest denomination, assuming that all of our what do you call that? The smallest unit you can use, in this case 1p. If you don't have that, that means you will have some change that you want to give, but then it's not possible to give that exact amount of change. If you did have a limited amount of coins, say in your cash box you didn't have a 1p, and you had to give, I don't know, 66p coin change, then that means this solution will not work, because you will yield a non-solution to this problem. So this is something to think about with greedy algorithms, because you can intuitively think of, okay, this is how I'm going to go about it. But for a particular solution, say in this solution, this works with at least 1p denomination, right? So that's something that, I guess, in my case, if I was in an algos interview, I'd go, yes, I'm assuming here that I have at least one P in the denomination, right? So someone might say this might be for a different country, and that country might have a different denomination set. As long as there's a 1P, the solution would work. But then it wouldn't if you don't have um, a 1P. So in this example, greedy algorithm can work for a specific set of conditions in this problem. So if we had a 1P, then it's possible to give all the solutions possible for a given change. But if we didn't have 1P, then that wouldn't be possible. So that's a little something that we need to think about when thinking about greedy algorithms. So yeah, I just said the answer. So so again, something to think about. Validating your greedy algorithm is very tricky. So the correctness is one thing, right? So as I said in the coins example, when you're thinking about the correctness of your algorithm, you have to think about, well, what if this denomination didn't exist, right? So that's one thing. The other thing is optimal validating if a greedy algorithm is optimal is also very difficult. So there's all sorts of like computer scientists and very smart people whose main purpose in life is to think about optimal answers to certain types of problems. So this is very tricky. So you have to like think through a good set of rigorous test cases, or think of ways to scope the problem. So as I said, in the context of an interview, you might say, for this solution, I want to say there has to be at least 1P coin in the denomination. So that's what I mean by scoping the problem. So the good news is greedy algorithms usually gets you close enough or good enough, right? So the technique actually gets you very far, even if it might not yield the optimal solution. But as we'll find out later, certain problems there are certain problems which we know about as a human race that we haven't found the optimal solution for, but with greedy algorithms gets you close enough to a good enough answer, right? So more about that later. So here, let's look at this other example, which is, I called it bags of flour. But in the internet, you can search this specific problem to be, they call this fractional bags. So let's talk about the problem here, the situation. So you're say you're some logistics company person. You're trying to deliver something. You're selling flowers in this case. So they come in bags. And each bag of flour has a different price. Say, and you have a knapsack with a capacity of 50 kilograms, right? And so you're selling these flowers. So what you want is to make the most profit, right? So to be able to carry the most value in your bag. So how can you fit in as much flour in your knapsack that allows you to carry the most value to sell? So in this case, you can sell partial bags of flour, right? So you can kind of take maybe some almond flour or some rice flour and put it in your knapsack. And here's my example. So have 3 types of flours, varying weights and varying amounts. So you know how do we do this, right? I mean, obviously the easiest way is you take a whole bag, and any bag that is less than your capacity, and put it in the bag. Now I want to make the most money, so I want to put the most value in my knapsack, right? So we want to look at the prices of these bags, right? So we said we had 50 kilograms. And so either one of these bags, we can decide. So again, we have the same pattern here. We have an array of options, and we want to decide what we want to put in the knapsack. So in this case, you have a 30 kilogram bag of tapioca flour for 120. So that's already a very big value, 120. And it's 30 kilograms, right? It means it can fit in our bag. And I don't have packaging, so I'm going to take that and put it in my knapsack. So that's my decision-making process. It's like, well, this is less than my capacity, and it's worth 120. So I put it in my bag. And so I have 2 bags left and I have 20 kilograms to go, right? So what's going to happen? Then I choose 20 kilograms bag of rice flour for 100. So this is very, again, I hope I'm making that point across now, that it's a very similar pattern of problem where you have a list of choices and you choose the best option available to you at that point in time. So yeah, there you go. So bag has a cost. So if you imagine cases where it doesn't perfectly fit, first bag we choose. So so first approach that I told you, where you go 30, 120, and 20, 100, is kind of like a naive approach, right? So we said, but is that like the most price you can put? Is that the most value you can put in the bag by just right? So let's start again for the bags of flour. So we said you're a delivery person, you have a knapsack with a capacity of 50 kilograms, and you want to sell these bags of flour. And you can sell partial bags of flour, right? So how can you fit as much flour in your knapsack that allows you to carry the most value to sell? And we went through a naive solution earlier before I got disconnected, or I wonder if you got to it, where we take the biggest bag available with the most price and choose that, as long as it's less than 50 kilograms. And then you go on, repeat until you have enough big bags to fit, but then and then put the rest partial weight of it, right? But then here in this case, you have a interesting property of the flour, bags of flour, which is the cost, or the pounds per kilogram of the flours. So it means some of these flours are more valuable than others. So it might make sense to actually think about the cost of the bags and use that as a way for us to decide which bag to go for. So if we actually sort the bags by cost, the first bag we choose is actually the one that has the best price to weight ratio. And then you fill the knapsack with whole bags because it's easy. You don't need to faff around with packaging flours. And then when you have capacity left, you can take part of a bag of the next most valuable flour. And so you can get a fraction of your available flour to fill the remaining weight of your knapsack. So that's kind of how we want to think about it. So again, when you're in the context of algorithm interviews, for example, if some detail is there in a problem, it's probably useful in terms of coming up with a good solution. In this case, cost is something not explicitly specified here, but it's actually something you can determine from the example. So what does that look like in code? So here I represented the bag of flour, the fractionable, the bag of flour as a class. So just call it, I'll give it a name, portion and price, and the cost. And in Python, you have this little nice trick, a neat trick, where you can override this operation called LT, which is, I think, stands for less than. And it allows you to automatically sort things of type item based on a property of that class. So again, very similar, very familiar to previous examples, right? We have an array of things. We sort them by cost so that we get the first bag we choose is the one with the best weight price ratio. And so we go through our list of things. Again, we take the whole item with the highest cost ratio and add them to the total value. So if this thing is less than or equal to the knapsack size, we can put them in our knapsack, right? And we add the weight to we add the weight of that thing we just took to the current weight, and we add the value. So we keep doing that until there's no more thing that can fit in our knapsack. So here we calculate the remaining weight of the knapsack from what we've put in the bag so far, and then add the total value of the fraction of the bag of flour. And then you return the total value. So in this case, the complexity of this problem is just the sorting. That's it. Right? So very simple approach and gets you good enough to solve the problem. So yeah, if you think about bags of flour, or this bags, fractional bags, actually there is a whole class of problems just about knapsacks, which is something I discovered while studying this problem. And so there is a variation of this previous problem where you cannot sell partial bags of flour. So what does that then look like, right? So we want to maximize again the cost, but then this time you cannot break up the pieces that you can put in the knapsack. So if you think about the brute force algorithm here, is that you're going to get different combinations of the bags that you can put in the knapsack and calculate the price of that. So in this case here, you're picking between several possibilities of what bags of flour you can put in the knapsack. So from all the subsets that you pick the maximum value subset. Now what's the implication of that? That means that you are trying to pick the best option multiple times from what is potentially a big amount of subsets. So if you have like lots of types of flours, actually you have to get many subsets in that flour. So this is not, so if you recognize this pattern, this is generally not solvable by a greedy algorithm, because at every step you have multiple options to pick from. In this case, subsets of your different combinations of your bags of flour. And they may or may not be the best choice. They might not end up with the best cost ratio. And the way you solve these types of problems, so if you have to pick the best option among pick the best option multiple times in a combination or combinatorial way, that is something that is solvable by what a different technique. It's what we call dynamic programming, and that's something we can. That's another topic that we'll be discussing in a different talk in this series. And I can send in this slide, there is a link to an article and a video explaining all sorts of knapsack problems. So why is this important? Why is it important for us to recognize what sort of knapsack problem is solvable by a greedy algorithm? So here we have a quick intro to what we call computational complexity. So recall that in a past discussion, in a past lecture in this series, we had a talk about algorithm complexity. And so, I used to think, okay, it's a way for us to quickly evaluate how long a problem will take to be solvable. But based on their complexity, an algorithm can be determined to be solvable in either polynomial or exponential time. Like, what is that? So polynomial time, what that means is basically it's the complexity of the algorithm is a polynomial. So if you go n squared, that's a polynomial, or n log n, that's a polynomial. So anything that is in polynomial time is generally good, and there exists solutions for problems where it is both correct and fast. So recall that greedy algorithms, validating them, whether they are correct, is quite tricky. So the non-fractional bags of flour is not actually, it's a type of problem that is not solvable in polynomial time. We have the other type of problem, which is called exponential time. This is generally bad. So time complexity grows really, really quickly. So in order to kind of solve these problems, we would have to make an approximation to come up with a good enough solution for these types of problems. So what does that mean, right? So here we looked at a few problems now in the previous example, and we kind of recognize a certain pattern of problems. And those problems have a time complexity, and those different types of time complexity are classified into two types, which is what we just described, P, problems that are solvable in polynomial time. Right, so if you want to think about what types of problems are P-type problems, we have basic arithmetic operations, right? Addition, subtraction, anything that is O of 1, right? Constant time complexity, or as I said, n squared, selection sort, that is solvable in polynomial time. So they are very easy to validate that they are correct, and there exist solutions that are quite fast. Then that brings you to the other type of problem, which are NP-type problems. These are problems that are solvable in non-deterministic polynomial time. So the example that I just described earlier, knapsack problem, where you cannot break down the bags of flour into fractions, this is solvable using what we call an exhaustive search, which I think we briefly discussed search in a previous talk in this series. But the next topic in this series, discussing graphs and trees, we'll be revisiting search problems again. And there we could possibly solve knapsack problem in that approach. But basically here, the key to recognizing whether something is a P or an NP is when you get to the complexity, if your variable is an exponent, so if your n is in the exponent, then that means it's likely to be an NP type problem. So the knapsack problem, you have different subsets of flowers, right? So if you had two bags of flour, then you have a few possible subsets. You know, maybe you have one, maybe you have two, maybe you have one or one the other, and that it quickly grows the more bags of flour you have to kind of evaluate. And so within NP, there's a set of problems called NP complete. Now, what is NP complete? So NP complete is, again, it's a very similar problem to the knapsack problem, where they're here, and specifically the example I'm going to talk about next, the traveling salesperson problem, there doesn't exist optimal solution to that problem, right? So here there are multiple ways of solving traveling salesperson problem, and here you can say, you know, using dynamic programming, you can say n squared times 2 to the n. Still, you have an n in the exponent, so never going to be a p-type problem. Or if you just use brute force, as in just consider all possible combinations of your routes, that is factorial complexity. So, as I said, these problems are really, really hard to solve. Usually there's no known efficient solution. But in many cases, NP-complete problems can have a solution that is approximate. So this is another technique you might hear or read when you read more about greedy algorithms, is called approximation. So it comes pretty close to being good enough. So if you recognize an NP problem, so these are likely to be a set type problem, like the knapsack. You have different sets of bags of flowers. Or traveling salesperson type problem, approximation can get you very far. And so why I've been talking about this, it's because greedy algorithms or a greedy approach is one way for us to solve NP-complete problems. They might not be the most optimal solution, but they're good enough, meaning you have a good guess of what could be the best option without it taking ages. So let's try and understand what this means a little bit by looking at the traveling salesperson problem, right? So the traveling salesperson problem is, well, you're a salesperson who needs to make trips to 4 different cities. What would your itinerary look like, right? So similar to the bags of flour problem, you can calculate the cost of all possible routes. So if you need to visit 2 cities, then your route is, you know, one to the other. But if you have 2 cities, you might go 3 cities, then you go maybe this way or that way. So that increases very, very quickly, factorial, right? And just to give you an idea, right? So imagine that you have a computer that can calculate the shortest route using permutations of all possible itineraries. For, you know, say you have a computer that can calculate 20 cities, and it takes 1 second to calculate that, right? If you had a 21 city problem, that would become 21 seconds, right? So immediately you can imagine, like, just adding 1 city increases the compute time for that problem. And then a 22 city problem will take about 7 minutes. But then a 30 city problem will take 3 million years to calculate. So it's like virtually impossible to find out the optimal solution, even using brute force approach, right? So we don't want to do that, right? We want to try and get to an answer using approximation. And so here, how would we think about this, the greedy way, the greedy algorithm approach, right? So in this case, so I've visualized the cities here, and this might look familiar to you as data structure. It's a is some type of graph. I'm not going to talk too much about graphs here because that's next session's topic. But here we pick a city, right? So say we have 4 cities here, and this is the distance between them, right? So again, with the algorithm, you're going to go through a set of things. In this case, it's a city, and you have some options. So here, if we're starting from 1, we have 3 options. We can go to city 2, city 4, or city 3. And in this case, I'm just going to make a decision and say I'm going to go for the shortest route here, because that's the best option at this stage. So here we got 3 options, and we pick 2 to go to. This is cheapest. So then we iterate to the next loop, and we go right. So we have only one way to go. So we go there. We go to 4, and here we get to 4, and we have a couple of options again, right? So we have 20 and 30 going to 1 and 3. Now here we know we've already been to 1, so we're not going to choose that one. So we're going to choose 3. So I guess here, you can start thinking about this in code. As you're going through the cities, you have to keep track of the cities you've visited, you've been to already, so that when you get to this case, you're not going to choose once you've been there before, and there's an option where you haven't been before. So you're going to choose 3 in this case. And then when you get to a place, right, there's only one way to go, and the place you are going is the place you started. So that's a property you can think of about the problem to say, okay, I'm done. I've gone through all the cities and eventually come up with the distance. Right? So in this case, treating it as a cost. Right? So that's just kind of how you want to think about the traveling salesperson problem through the greedy way. Now you can learn more about this problem using, if you search the term nearest neighbors. So there's a lot of problems that look like this, where you choose the nearest neighbor to make a decision. And I linked here some references so that you can read more about this stuff. So the chapter 8 of Grokking Algorithms book talks more about, also talks about approximation. They also use the bags of flour example there, but they call it that there in that example you're a thief and you are stealing items from a house, and you have to steal as fast as possible and maximize for the price. Very similar type of problem. If you want to learn more about computational complexity, there's a video here I linked. It's very, very good. Explanation is very approachable. Might need a little bit of math, but I think it's manageable. But and yeah, there's more knapsack problems. There's so many. We can probably do a whole topic just on knapsack problems. There you go. That is it. Yeah, feel free to code up the traveling salesperson solution. And for all the other examples, you can find all the code in GitHub if you want to take a look. And that is it. That is the end of my introduction to greedy algorithms.
Thank you very much, Jamica. This is the end of our theoretical part. And once I kick my cat out of my desk, we proceed to breakout rooms.